It came from deep space. A burst of radio waves, extraordinarily powerful, extraordinarily brief, lasting less than a millisecond, gone before most instruments even had time to register it fully. And it carried more energy in that fraction of a second than our sun releases in 3 days. When scientists first detected it, they checked the instruments, then checked them again. They looked for terrestrial interference, for satellites, for aircraft, for any local, explainable source that might account for a signal this powerful, arriving so suddenly from the direction of a galaxy billions of light years away. They found nothing local. The signal was real. It was cosmic. It came from somewhere out there. And despite years of study, thousands of research papers, and the combined effort of some of the best minds in astrophysics, nobody can fully explain where it came from, what produced it, or why. This is not an isolated case. The universe is full of signals that defy explanation, signals that arrived unexpected, that broke the patterns our instruments were designed to detect, that refuse to fit neatly into any category our science has developed. Some of them have been detected once and never again. Some repeat, with a disturbing regularity that raises more questions than it answers. Some come from directions in space where nothing we can observe should be producing them. None of them are proof of anything supernatural, but all of them are proof of something more honest and more exciting than the supernatural. Proof that the universe is still hiding things from us, enormous things. Things that our current understanding of physics cannot account for. This is the story of the signals scientists still cannot explain, and following the evidence, one mystery at a time, takes us to the strangest, most extraordinary corners of the cosmos, and sometimes, unsettlingly, back to our own galactic neighborhood. It begins on the night of August 15, 1977. At the Big Ear Radio Telescope at Ohio State University, a volunteer astronomer named Jerry Emmon is reviewing a computer printout of radio telescope data. Routine work, looking for patterns in the noise, the kind of careful, methodical, largely uneventful work that makes up most of science. Then he sees it. A sequence of characters in the printout that represents a radio signal so strong, so perfectly matching the profile of what scientists had theorized an extraterrestrial transmission might look like, that Emmon does the only thing that feels adequate in the moment. He circles it in red pen and writes a single word in the margin. Wow. The wow signal, as it has been known ever since, lasted exactly 72 seconds, the maximum duration Big Ear could observe any signal given its fixed field of view and Earth's rotation. It appeared once, clearly, unmistakably, in a narrow band of radio frequency remarkably close to 1420 megahertz. That frequency is significant. 1420 megahertz is the frequency at which neutral hydrogen, the most abundant element in the universe, naturally emits radio waves. Scientists had long theorized that if any intelligent civilization wanted to broadcast a signal that another civilization might recognize as non-natural, they might choose this frequency. It is a cosmic landmark, a universal signpost. The wow signal arrived at almost exactly that frequency. It was also narrowband, meaning it occupied a very specific, very narrow range of frequencies rather than the broad smear that natural astrophysical processes typically produce. Narrowband signals are characteristic of artificial transmitters, of technology rather than nature. For 72 seconds, everything about this signal matched the profile of what scientists had hoped to detect for decades. And then, it was gone. It has never been detected again. Not once, not in the nearly 50 years since that August night. Dozens of searches have pointed instruments at the same region of sky. Thousands of hours of observation. Nothing. No repeat. No follow-up. No second transmission. Some scientists have proposed natural explanations. Comets, unusual celestial mechanics, hydrogen clouds moving in unexpected ways. These explanations have been debated.
contested, and remain inconclusive. The wow signal does not fit neatly into any natural category we have identified. And it does not fit neatly into any artificial one either, because whatever produced it, if it was artificial, never transmitted again. It arrived, it was witnessed by exactly the right instrument in exactly the right orientation at exactly the right moment, and it left, leaving behind one circled printout, one handwritten word, and one of the most enduring mysteries in the history of the search for life beyond Earth. But as extraordinary as the wow signal is, it is not the only unexplained signal the universe has sent us. In the decades since 1977, something else has emerged from the data. Something that repeats. Something that does not have the courtesy to be a one-time anomaly. Something that scientists are still scrambling to explain.
In 2007, astronomers analyzing archival data from the Parkes Radio Telescope in Australia found something buried in old observations from 2001. A burst of radio waves, milliseconds long, extraordinarily bright, originating from far outside our galaxy. They called it a fast radio burst. At the time, it was a curiosity, a single detection in archival data. It might have been an instrument artifact. It might have been a one-time cosmic event. Nobody was certain. Then, more were found. And more. Today, scientists have detected over 1,000 fast radio bursts from locations scattered across the sky, each one an intense millisecond duration flash of radio energy, each one carrying enormous amounts of power, each one coming from cosmological distances, galaxies hundreds of millions, sometimes billions of light years away. The total energy released in a single fast radio burst in a millisecond can equal the energy our sun produces over 3 entire days. In 1 millisecond. The rate at which energy must be concentrated and released to produce that kind of output in that kind of time frame requires physical conditions that push against the limits of what we understand about astrophysics. And then, in 2020, something happened that both clarified and deepened the mystery. A fast radio burst was detected from inside our own galaxy, from a magnetar, a type of highly magnetized neutron star called SGR 1935 plus 2154, located roughly 30,000 light-years from Earth, well within the Milky Way itself. This was the first time a fast radio burst had been definitively linked to a known type of astronomical object. It strongly suggested that at least some fast radio bursts are produced by magnetars, by the violent, energetic flares generated when the extreme magnetic fields of these objects shift and crack. For a moment, it seemed like the mystery was solved, but it was not solved. It was complicated. Because here is the problem. The fast radio burst from SGR 1935 plus 2154 was, by the standards of fast radio bursts, relatively weak, comparatively modest in its energy output. Many of the extragalactic fast radio bursts detected from other galaxies are thousands of times more powerful than anything a typical magnetar's flare should be capable of producing, which means magnetars may explain some fast radio bursts, perhaps many of them, but the most powerful ones, the most energetic, the most extreme events in this class remain unexplained. And then there are the repeaters. Most fast radio bursts are detected once and never again. Like the wow signal, they arrive, they are measured, and they vanish. But a small number repeat. They fire multiple times from the same location, sometimes with patterns, sometimes irregularly, with intervals that range from seconds to years. One repeating source, called FRB 20121102A, fired hundreds of times from the same galaxy, hundreds of distinct bursts, some of them arriving in clusters, some of them showing patterns in their timing that have prompted intense scientific debate about whether the pattern is meaningful or coincidental. Another repeating source, FRB 20180916B, bursts on a roughly 16-day cycle, active for 4 days, then quiet for 12, then active again, with a regularity that suggests a physical mechanism creating that rhythm. What mechanism?
Nobody is certain. Orbital dynamics, a precessing neutron star, a companion object creating periodic changes in the environment around the source. Multiple candidate explanations exist, and none has been definitively confirmed. The repeating fast radio bursts are the most tantalizing signals in modern astronomy, not because they suggest intelligence, there is no evidence for that, and scientists are appropriately cautious about such claims, but because their repetition means we can study them. We can observe them multiple times with multiple instruments, gathering data that single burst events cannot provide. We can measure their timing, their spectral properties, their polarization. We can piece together a picture of whatever is producing them. And that picture, so far, refuses to fit any single clean explanation.
We have been listening to the universe for a long time now. Since the first radio telescopes were pointed at the sky in the early 20th century, since the first systematic searches for signals of extraterrestrial origin began in the 1960s, since we started launching spacecraft with instruments capable of detecting the faintest whispers of radio, plasma, and electromagnetic activity in the space between the planets and the stars. And what we have found is a universe that is not silent. It hums and crackles and bursts and pulses with electromagnetic activity, with signals of every kind, many of them explained: the radio emissions of pulsars, the thermal radiation of stellar nurseries, the X-rays of black hole accretion disks, understood, cataloged, filed. But some of them are not explained. Not yet. The wow signal. The fast radio bursts, especially the most powerful and the repeating ones, the ultra-high energy cosmic rays arriving from impossible distances, and a long tail of anomalies, curiosities, and detected phenomena that science has logged carefully and is still working to understand. What should we make of these unexplained signals? The honest answer requires resisting two equally tempting but equally wrong responses. The first wrong response is to leap to extraordinary conclusions, to say, we cannot explain this, therefore it must be something beyond current science, beyond known physics, beyond the natural universe entirely. This is the response that turns mystery into mythology. It feels satisfying in the moment, but closes the door on genuine understanding. The second wrong response is the opposite. To dismiss, to say, we cannot explain this yet, but we will, and it will certainly turn out to be mundane. To assume, without evidence, that every unexplained signal will resolve into something comfortable and familiar once we look hard enough. This response is also wrong because it imposes our expectations on the universe, and the universe, as we have seen repeatedly, does not care about our expectations. The right response is harder, and rarer, and more rewarding. It is to sit with the not knowing, to hold the mystery honestly, to say, this signal does not fit our models. This means either our models are incomplete, which they certainly are, or the universe contains something we have not yet encountered and do not yet understand. And both of those possibilities are extraordinary. Because here is the truth about unexplained signals. Whether they turn out to be new natural phenomena, exotic astrophysical processes we have not yet identified, or something else entirely, they are pointing us forward. They are the edges of the map. Every unexplained signal is a marker at the boundary of human knowledge, a flag planted in the territory where our understanding runs out and the unknown begins. And the unknown is not an absence. It is not emptiness. It is the next chapter, the next discovery, the next paradigm shift waiting to happen. The scientists who study fast radio bursts are not frightened by the mystery, they are energized by it. They build better instruments, design more sensitive detectors, propose new theoretical frameworks, challenge old assumptions, because the signal demands it, because something out there is doing something that requires explanation, and the job of science is to find that explanation. The wow signal arrived once on an August night in 1977. Nobody knows what sent it, but it changed something. It changed how seriously we take the search, how carefully we listen,
how much effort we invest in building the instruments and training the minds that might, one day, hear the next one and finally understand what it is saying. The universe is full of signals. Most of them we understand, some of them we do not. And the ones we do not understand are the most important ones of all, because they are the universe's way of reminding us that the story is not finished, that the next chapter is already being written, in signals we have not yet received, from sources we have not yet imagined, traveling toward us right now at the speed of light. We just have to keep listening.
Fast radio bursts and the wow signal are the most famous unexplained signals. But they are not alone. The universe has a habit of producing phenomena that arrive uninvited and refuse to explain themselves. Consider the ultra-high energy cosmic rays. Cosmic rays are not radio signals, they are particles, protons and atomic nuclei, traveling through space at extraordinary speeds. Most cosmic rays arrive at Earth with energies that, while impressive, fall within ranges that known astrophysical processes can plausibly account for. But ultra-high energy cosmic rays are different. They arrive with energies so extreme, millions of times higher than anything produced by the most powerful particle accelerator ever built by humanity, that their very existence raises profound questions. There is a theoretical upper limit to the energy a cosmic ray can have while still traveling cosmological distances, called the GZK limit, after the physicists who calculated it. At energies above this limit, cosmic rays should interact with the cosmic microwave background radiation, the ancient afterglow of the Big Bang that fills all of space, and lose energy rapidly. They should not be able to travel more than a few 100 million light-years before degrading below the limit. And yet, ultra-high energy cosmic rays arrive at Earth from directions pointing back to sources much farther away, sources that should not be able to produce particles energetic enough to reach us. What is accelerating these particles to such extraordinary energies? What mechanism exists in the universe capable of producing something the LHC, the most powerful particle accelerator ever built, cannot even approach? The answer is not known. Or consider the anomalous signals detected in the data of NASA's Pioneer spacecraft. Pioneer 10 and Pioneer 11, launched in the 1970s, were tracked carefully as they journeyed into the outer solar system and beyond. For decades, their actual positions, measured by their radio signals, deviated subtly but consistently from where orbital calculations said they should be. Something was slowing them down. Something not accounted for by any known force, a tiny, persistent, directional acceleration toward the sun that no known physics could explain. This became known as the Pioneer anomaly. It attracted serious scientific attention for years. Multiple exotic explanations were proposed, including modifications to the law of gravity itself. Eventually, a more mundane explanation emerged: thermal radiation from the spacecraft's own power systems, pushing against them like a gentle but persistent wind of photons. An explanation that satisfied most scientists, though some continue to debate its completeness. But the Pioneer anomaly is instructive precisely because of what it shows us. Even ordinary spacecraft, operating in the relatively well-mapped environment of our own solar system, can produce signals and behaviors that take decades to explain. The universe is large, and we are working with incomplete information. Every unexplained signal is a data point, a piece of a puzzle we cannot yet see the full shape of, a hint that the map we have drawn does not yet match the territory. And sometimes, very rarely, but sometimes, the territory turns out to be far more surprising than anyone predicted.